So awesome. Thank you. No problem. So before I start, I want to give you, I'm sure you've heard of University of Maryland, but a very quick, like University of Illinois is the flagship university of the University of Illinois systems. Maryland is also, University of Maryland is the flagship institution of the University of Maryland, system of Maryland, right? And Terrapin, you can see this. We are very close to Washington, D.C. We are, I think, like 7 miles from Northeast D.C. So not that far. And if you're in D.C. area, you're more than welcome to, come and visit us. So before I joined Maryland, there was not research program in power electronics at Maryland, so I started everything and built up everything from scratch. Right now, I have 10 PhD students, 1 postdoc in my research group, and I'm in the process of hiring 2 more postdocs. So this is our current research groups, and then these are some of alumni from my research group that you can see they're everywhere in the world. There are, like, we graduated 9 PhD students, 10 master's students, and a lot of undergraduate students within this time period. Just after a brief introduction about my research at Maryland, let's talk about power electronics. So all of you are familiar with the power electronics. I want this topic to be more general, so it's more attractive not only to power electronics students and faculty, but also to people who work in power system and general subjects. So I'm not going to focus on detail of implementation. I'm going to more focus on the topics and what are the areas that we are covering. So power electronics is going through a major restructuring, right? You can see tons of new opportunities are coming up. One of the important things, there are new emerging technologies in power electronics. You're familiar or at least heard of wide bandgap devices, right? So with the introduction of these wide bandgap devices like silicon carbide, gallium nitride, and diamond-based semiconductor, we see there are new kind of design opportunities are happening, new kind of gate drive, new kind of circuit topologies compatible with these, We also need to be able to, have really better performance capacitor. We need to have really good performing magnetic components. So all these new technologies, they are helping us to create new design techniques, right? So we need to look at new design approaches. So in the past, power electronic engineers, they design their circuits based on heuristics, based on the knowledge. They go and design, they choose, okay, capacitor, inductance value, switch number, whatever it is, and then they design a circuit based on the heuristic, based on the experience that they have. But now even the design methodologies for power converters is completely changing. We're not only looking at normal design, but we want to look into, if you want to have a real optimal design, you need to have a multi-objective optimization design, right, for power electronic. But it's a new area that some researchers, they are looking into it. Or you want to design for reliability, not just design for operation in the normal condition, or design for packaging. So, and these new, emerging technologies and emerging design techniques are enabling tons of new applications that in the past, we didn't have these applications. They didn't need power electronics. Like if you look at it, renewable energies, transportation electrification, smart grids, robotics, and micro-robotics, in particular micro-robotics, biomedical systems, cloud computing and data centers, communication system, aerospace, defense system, cryogenic systems, different actuating system, pyroelectric energy. I don't know if you're familiar, have you heard of pyroelectric on top of piezoelectric, electromagnetic, electrostatic, or high pressure systems. If you're doing drilling, you need very high speed system and high speed drives for those, or extreme temperature applications. Right now we need our power electronic devices to be able to operate in extreme temperature from negative 150 degrees Celsius in, let's say, on the surface of Mars to positive 120 degrees Celsius. So these are creating new opportunities for power electronics. But my topic and my research at Maryland addresses some of these challenges. So my research is mostly focused on transportation electrification, power electronic for transportation electrification, and we've done a lot of work on hybrid electric cars, and also we have been working continuously with Boeing on more electric aircraft, which is, I'm going to briefly mention about that. Also, we have started doing a lot of work on highly reliable and low-cost manufacturable PV microinverters. And we've done a lot of work on miniaturization of power electronics for micro-robotics, energy harvesting, data centers, and Internet of Things. These are the topics that we cover. These are the most of the topics, not all the topics that we've worked on, because we've done also a lot of work on space applications, which I would just briefly mention. Now, if we look at now power electronics for electric vehicles, there are tons of opportunities for power electronics in electric vehicles. What are those? First of all, these are improving by these are expanding by the increasing number of these electric cars in the world. This graph shows you the number of electric cars sold by most popular electric cars sold by in 2017 in North America. And you can see, for example, Tesla Model S has sold the highest number. And I have another slide which shows the top-selling PHEVs, plug-in hybrid electric vehicles, in the North America in 2017. And you see these numbers are increasing. In fact, if you look at the statistics, in 2017, we had about 1.2 million new electric car sales in the world. And the US, I think, to the best of my knowledge, contributed about 250,000 of those. And since 2000 till 2015, US used to be the leader. Now China is taking over. It started to take over from 2016. I think more than 700,000 in 2017 new electric cars have been sold in China. And I did some research and I looked at the battery capacity and charger capacity and electric mile range, all electric mile range of these cars, the popular ones. And if you look at the EV range of commercially available electric vehicles in 2017, you will see they go from 80 miles to 335 miles. So for us, in my opinion, to have electric cars to be, to go popular and become mainstream, we need electric cars with more than 300-mile range. That would put EVs in a condition that will be more comparable to, driving range of the normal car, internal combustion engine.
Does this correlate with top sellers, or this is just because you didn't have any other way to arrange them?
No, this is just because I couldn't fit all of them, so that's how I put it in this way. Otherwise, this is top sell.
As a top seller?
Yeah, Model S, these two. These are both Model S.
Okay.
So then I looked at their onboard charger, because this talk is more on onboard chargers. So I was like, let me look at these, their onboard charging power levels, and then see what is going on. So I looked at these cars, which I showed their pictures there. So most of the EVs, pure electric cars, they have a 6.6, 7 point, whatever. This is like almost same level onboard charger. And then Tesla has 17.2 or 19.2 kilowatt, which is still single phase. And then I looked at the onboard charger for PHEVs. I looked at those and I noticed they're mostly 3.3 kilowatt, right? Because their battery is smaller, right? Because they have an additional engine in there. So if you have a lower power onboard charger, that's enough to charge the battery in a reasonable amount of time if you're using level 2 charging. And I guess you know what is level 1, level 2, level 3. If you don't, in case, so level 1, anything based on SAE J1772, if your power level is less than 3.3 kilowatt, no, if it's less than 1.92 kilowatt, that's level 1. Anything beyond 1.92 up to 19.2 is level 2. Anything beyond 19.2 becomes level 3 charging, okay, fast charging. Most of the times, up to level 1 and level 2 chargers, they're on board of the vehicle. Anything beyond 19.2 goes off-board charging. It's a DC fast charging approach. So anyway, so I looked at these cars and their onboard chargers. And before I talk about the onboard chargers, I want to show you what are the opportunities for us as electrical engineers that we can contribute. There are tons of components in an inside the electric vehicle that they can contribute and make a lot of contributions. One is the inverters. Inverters, they have traditionally not been efficient, but with the introduction of the wide bandgap devices, there are opportunities for us to improve them. Then another thing is chargers. As I said, there are two kinds of chargers. You can either have onboard chargers or off-board chargers. And then those could be also level 1, level 2, level 3, and they could be also wireless chargings, right? There is propulsion DC-DC converter. Besides the inverter, some electric cars, they have an additional DC-DC converter between the battery and the inverter, right? Propulsion inverter. Then energy storage system. You have a battery. You have battery management system there, right? That has a lot of power electronics, cell balancing, cell equalization, and all those things. And then, besides that, if you have a hybrid energy storage system, that is additional power electronics, right? You need a DC-DC converter between your battery and supercapacitor. And this by itself, this battery supercapacitor has a huge, that's in my opinion, long topic that I can talk about it at least half a day if I want to get into that. And a lot of people they have done research on this battery supercapacitor topic, which differ for different application. And for electric vehicle application, I'll show you what we did at the end. Let me get back to this later because I don't want to spend so much of time. And then on top of it, electric machines. Traditionally, electric machines, I mean, people have used induction machines, right? Now they are looking at the permanent magnet synchronous machines. And then, you know, permanent magnets are rare earth material. So now people are looking at kind of hybrid or hybrid SR switch reluctance permanent magnet, or they're trying to reduce the amount of the permanent magnets on the electric machine so they are less rare earth material dependent. So that's additional opportunity for us. So, and then, as I said, in terms of charger, off-board charger, underground wireless charger. And on top of these, there's additional DC-DC converter for auxiliary power module inside the car, right? You have it, every car has a 400-volt battery, and then every car, I mean, electric cars, they have 400-volt battery, and they have a 12-volt battery as well. So there's a DC-DC converter in between to step down 400 to 12. That's additional. So all these opportunities for us to improve and do a lot of contributions here. A few years ago, in fact, it's interesting because traditionally, auto industry has been driven by mechanical engineers. They used to have a lot of hires in mechanical engineering. And then I get an email from one of the directors of one of the big three, and then they tell me that they have 78 positions, or 178, which is something on hybrid, their hybrid propulsion division. Means how much need there is for power electronic engineers in auto industry. So we can contribute a lot of those. As I said, my topic is on onboard chargers. These are two of the prototypes was designed in my lab. Let's move on and then see what are the perspectives for onboard chargers. And then I'm going to go a little bit more on the technical part of it. So everybody has heard of onboard chargers, right? Right? Onboard chargers is a simple charger. You have a cell phone charger, you have a laptop charger, you have an onboard charger for the electric vehicle. You don't need to carry it with you anywhere. So if you look at the structure of an onboard charger, normally an onboard charger has 3 stages. First stage is an EMI stage, right? Second stage is an AC-DC power factor correction and rectification stage. And the third stage is a DC-DC stage, right? And then there are so many magnetic components there, right? So in my opinion, and there are most of the chargers that you can see there are unidirectional. So in my opinion, first of all, we need to have bidirectional chargers, right? Because eventually, electric cars, when they become more and more popular, there are tons of batteries there. That battery could be utilized as a support for the grid or different applications. So next generation of onboard chargers, they need to be bidirectional. 2, there are a lot of magnetic components in these different stages. So in my opinion, next generation of onboard chargers, they need to kind of use integrated magnetic structures. So for example, think about a CLLC converter, or if you're, again, power electronic, you know what is CLLC converter, right? And if you think about a dual active bridge converter, right, or a phase shift full bridge converter, normally you have a transformer magnetic component plus another leakage inductance there, or a resonant inductor there, right? Normally you have different, because when you're designing a CLLC converter, you need a large inductor there, right, to create your inductance for leakage or resonant inductor. So can you integrate inside the transformer? If you can integrate that, you get rid of one of the components. You improve the efficiency and you reduce the volume.
Can you explain that bidirectional, what you mean by that? Because
sure.
Don't we, right now we have regenerative braking, and so the power goes in and out of the battery.
Sure. No, bidirectional means when it is stationary. Bidirectional charging when the car is not moving. Not during the driving of the car. So when the car is stationary, not only you can charge the battery from the grid, vehicle to grid, but also the grid to vehicle discharge. That's what I mean.
So it's that one particular application.
Yes, it's the charger part. We don't care about the propulsion machine side at all. So that regenerative braking happens during driving of the car. So beside. And then another important thing, in my opinion, we want to be able to charge deeply depleted battery packs. Most of the chargers you see right now, they are designed to charge battery from 200 or 250 volt up to 420 volt. So if the voltage of the battery drops below that, we say battery is dead. So this is what we call it deeply depleted. When the battery, let's say it's a single cell. If you look at a single cell, the voltage can go from 2.5 from a lithium-ion battery to 4.2. If it drops to 1 volt, battery is dead. So can we design chargers that can charge the battery from 1 volt, even deeply depleted batteries? there are ways that you can actuate, and even though your efficiency is going to be bad, really bad, but at least you can charge it. Then, if we can improve the efficiency over the wide range of the voltage, not only if you look at the chargers, most of the papers that you read, they say, oh, the efficiency of my charger is 92.8%, whatever, I'm just giving an example. But that is only at the full load. But when you're charging a battery, you're doing constant current, constant voltage charging, that efficiency, that whatever 92.4, it doesn't happen for the entire range of the charging. It happens only, let's say, 30% of the time, right? The rest of it, your efficiency is how much? 80%. Nobody claims that. Nobody even reports that. So we need to improve the efficiency over the wide range, not only at full load. Also, I think it's a good idea to look into new generation of onboard chargers called reduced stage onboard chargers. Instead of having EMI, AC, DC, 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 can we get rid of one of those stages? Because those stages, they contribute to power density, they contribute to loss as well, right? So can we get rid of those? There are ways to do that. And then another thing which is, in my opinion, is going to be, happen, and we had a workshop, in fact, and a lot of people from industry, they mentioned this, integrated power electronic interface, not only chargers. So I showed you so many converters on board of a car, right? Can we kind of integrate them and then make sure that we have one converter which does the functionality for 2, 3 of them? There's been a lot of investment in battery technology, but not enough, in my opinion, and there's room, huge room in power electronic industry. So, because my topic is on chargers, I'm going to talk about low power integrated chargers and high power integrated chargers. But again, this is not the only integration, only possible integration. There are tons of other opportunities for integration. And beside that, if we want to reduce the weight and volume, and if we want to really improve the power density, we need to think about megahertz level chargers. If we go to megahertz, we can reduce the size significantly. But that has its own challenges, which I'm going to talk later. So towards achieving some of those goals that I showed you, those are my prospects for next generation of onboard charger. Towards achieving those, this is a first work in my research where we conducted. We looked into a concept of parallel resonant stage onboard charger. Parallel resonant stage, I mean, is nothing in particular. You have, this is your PFC stage followed by 2 DC-DC stages in parallel. Okay. So what happens is normally, how many options do we have to design the DC-DC stage? 4 normally, right? If you want to do resonant, in fact, maybe 5, right? If you can do dual active bridge phase shift, right? Dual active bridge, you can do SRC, you can do LLC, you can do LCC, or you can do LLC, right? These are the options that you have. And people have done a lot of research in this, and they have noticed LLC is the best DC-DC converter, second stage converter, to give you the best voltage regulation possible for the battery, because the battery voltage, depending on the state of the charge of the battery, can go from 200 volt to 400 to a large range. And if you use an SRC, which has a better efficiency, the problem would be you cannot regulate the voltage. So what if we combine 2 of them in parallel? Instead of having one SRC or LLC, we have one SRC, one LLC in parallel, and we optimize them depending on the distribution power between them and depending on the charge profile of the battery, right? Nobody has done this, to the best of my knowledge. We did this, and we haven't even published this yet. We did a couple of years ago, but we didn't publish this. We were so busy. And we designed this. So in fact, this represents a 3.3 kilowatt onboard charger. This is not an optimized design. This is a first stage, AC-DC. The second stage has 2, one SRC, one LLC, right? And then this is our control board. I should a little bit change this figure. It shows too big. It's not really big. This whole height is the size of a mug. It's not that big. Okay, this here looks too big.
We have a picture of that with the mug next to it.
I should do that. I should take a picture of that with the mug next to it, showing that this is not really big.
And the logo should have a Maryland picture.
Correct.
Yes, the mug's logo.
If you want to do some advertising of our program, we can give you an Illinois one.
Exactly. We can put one in here, one there. So it's so we designed this to look at the efficiency, and then we compared the efficiency of this with. So the way that we controlled these 2 converters to operate, it was we didn't do any optimization in terms of the design. We only designed the 1.1 kilowatt LLC and the 2.2 kilowatt SRC to design a 3.3 kilowatt. But I'm sure there is a lot of room to optimize this and see what is the really best, depending on the battery state of charge, what is the best optimization here. We did that. And then we compared with the state-of-the-art published with this group by Delta Q Corporation. Delta Q is one of the companies that they design onboard chargers for a lot of applications, automotive or industrial design. And we compared with that, and we showed that if you do this and you run normally your LLC all the time, because LLC gives you the best kind of efficiency when you're operated in the full load, and SRC, you bring it in whenever you need more power than 1.1 kilowatt. Okay? And then you can improve the efficiency at the full load by about 1%, 1.3% at the most. But the important thing is in the light load, we can improve the efficiency at least 10%. That is a huge improvement. In fact, we did some analysis and noticed if you improve the efficiency by 10% during charging the battery, if you charge your electric car battery once a day, that will reduce your electricity bill by 1 month over the entire year. That 10% improvement. Or average 8% over the entire thing. That is from even, I know that most people might not even care about that 1 month electricity bill, or maybe auto manufacturers wouldn't care about because they're selling it. But I think from a consumer perspective, that is useful. Then after doing that research, we thought of, okay, what else we can do? If we look at the powertrain of a car, this is a powertrain of a car, right? This is a plug-in hybrid electric car, right? Engine, starter generator, transmission, propulsion machine, inverter. We might have a DC-DC converter here between this and the high voltage battery, which in this picture I haven't shown it. Small battery, 12 volt, 400 volt big battery, onboard charger, step down, auxiliary power module. So can we, as I said, can we integrate some of them and make them smaller? So this is an OBC and this is an APN. If we can integrate these two, each of them, let's say this is designed, let's say for a plug-in hybrid, this is a plug-in hybrid, 3.3 kilowatt, and this could be, I don't know, 2.5 kilowatt. If we can integrate these two, you can reduce the volume by 50%, weight by 50%, cost by 50%, and if you can make it bidirectional, better, and it's very attractive. So we did some research on this. As I said, these are two independent units, and they are bulky, heavy, expensive, and important thing, these components on board of the car, they communicate over a protocol called CAN bus, Control Area Network Communication Protocol. And those CAN bus protocols, they are proprietary to every auto manufacturer. So if you're doing any kind of after shelf conversion, you need to go through it and you don't have access to none of those information. But if you can integrate them, they are local. They don't need to go through CAN bus community. They can locally communicate with each other. And then another thing is these efficiency, as I said, in the light load is low and also not unidirectional, not compatible with the future smart grid technologies. So if integrating that gives you the integrated efficiency and those advantages. So this is the very first prototype we designed. It's nothing complicated except the first stage is a totem pole bridgeless interleaved AC-DC converter, bidirectional. The second stage, this one is a Resonant. Initially, we designed this with silicon carbide, and it's a Resonant single input, double output converter with a very simple transformer, with a 3-winding transformer. So our input of the transformer is connected to the AC-DC stage, and then output has a 400 volt output and a 12 volt output. So in fact, you have a foil in the third tertiary winding is only one turn, and then the other windings are right there, so primary and second. It's nothing complicated in the design. I mean, of course, control has a lot of challenges in it. Not that it's very straightforward, but it's not topology is not difficult. And we tested this under different loading conditions, from variable input, universal input grid voltages from 85 volt AC up to 265 volt AC, and we looked at the efficiency improvements. And we compared it with the state of the art. As you can see, the state of the art in our measurement has been improved about 1 to 2%. We showed this, but our main contribution is not on AC/DC stage; it's more on the DC/DC stage. And these are the parameters that after designing the DC/DC stage we got. I don't want to go to the depth of how did we calculate it. These are I guess more detail you can find in our papers. We have published this. But we also, again, look at the efficiency curves and those make sure that ZVS happens during the turn on and turn off of switches, zero voltage switching, because we looked at, you can simply, when you're designing a CLLC converter, what you can do, you can look into the impedance versus frequency, and you can the voltage gain versus frequency, and then you can make sure that you're always doing zero voltage switching in the primary, and in the secondary, you're doing a zero current switching, to make sure that you reduce the losses. So this figure only shows that we are ensuring the zero voltage switching happening, and then shows the efficiency number in different modes of operation that we have: grid to vehicle, vehicle to grid, and high voltage to low voltage, means 412 watt. Still, this number needs to be improved, but the reason we had not really promising efficiency in here was because we were using CLLC topology in here, and then half-bridge CLLC topology. But for high-power application, I think after this research, we have learned that the best topology would be full-bridge topology, not half-bridge topology, because when you do half-bridge topology, the current stress goes up, and you need to overrate your capacitors, and also your switches. And that also creates a little bit heating problem in your transformer because of the higher current, double current, in comparison to full-bridge. Then we decided to redesign this, going with a full-bridge topology. And then we have also noticed that if you're designing CLLC topology is not the best thing for higher power. Maybe for 3.3 kilowatt it will work, but if you want to go to 6.6 kilowatt, and auto industry, in my opinion, right now is moving to higher, in fact, charging levels. Right now, if you see all the onboard chargers are 6.6 kilowatt, it's presumed that it's going to go to around 11 kilowatt. Future, next couple of years, in fact, like 3 to 5 years, it's going to be 11 kilowatt. So if you go to 11 kilowatt, then CLLC is not going to be the best topology because of, and also if you have a tertiary winding, because it's going to have really high switching stress on the components, and also switching losses. So after this, so another thing we have noticed is interesting in this integration. If you're using a CLLC topology, you cannot charge the high voltage battery and low voltage battery at the same time. Okay, so what you need to do when you're connected to the grid, you only need to charge the high voltage battery. When you're driving, you can charge low voltage battery from the high voltage battery. But what happens during preconditioning? If you're, for example, that both the battery state of the charges are low, and you're at home, and then you want to go get into the car, right? And it's a very cold condition. You need to first turn on the LV battery to warm up the HV system. If you cannot do it, your system is not going to start working. So then we noticed we cannot do that with the LLC topology. We need to go with TAB, triple active bridge, or DAB. We traditionally have dual active bridge. We need to make it triple active bridge topology to ensure that we can have simultaneous charge capability, to enable us, both HV batteries can be charged at the same time that we do preconditioning, and also we can provide power to auxiliary loads. And because these auxiliary loads, they also provide power to all the microcontroller and all the electronic devices on board of the vehicle. So, this new topology that we looked at it should be capable of doing all these modes of operation: grid to vehicle charging, vehicle to grid discharging, high voltage to low voltage battery charging, and grid to both. And grid to low voltage. Sometimes you only need to do both. Oh, and also grid to both of the charging. So we looked at this topology for that, which, as I mentioned, it's a triple active bridge topology. Again, at the beginning is a totem pole phase shift full bridge. It's an interleaved as well. So we have a slow leg, and then we have fast legs. And then we have 3 full bridges in here. One of the voltages goes from 200 to 450. One of them goes from, let's say, 8 volt to 15 volt. It could go lower than 10 volt. Now, the control of this, it becomes a little bit challenging problem. Not too difficult, but it could become challenging because now you have 3 sources here. This is a source when you're charging from the grid. This is another source. This is another source, right? So inherently, there's going to be a power flow between this bus to this bus, right? You cannot say, oh, I'm going to only have this power flow for this and this. We will make this power 0 because there's going to be a power flow there. Now, one of the challenges is how you can minimize the power flow and reactive power, which is circulating between these three sources. So we did some work on that. And my student came up with a method to minimize this loss and to control this. So in fact, you have 5 control variables here. In fact, if you suppose that this phase, let's call it Q1, is 0. The phase angle of that one is 0. And then the phase angle between the fundamental frequency of this phase and this phase is phi 2, and the phase angle between the fundamental frequency of this bridge and this bridge is phi 3. So that's two control variable. Phi 2, phi 3 is the control between the fundamental frequency. And then also you define this delta 1, delta 2, delta 3, which deltas are the time that these pulse width modulations, they are 0. So that gives you 3 more variables. By controlling this 5 variable, you can control the current flow and power flow here, and you can control the current flow and, current and voltage here, right? You can control this. Initially, we did a lot of investigation. We looked into different topologies. It was initially, we put these deltas equal to 0, all of them, to make sure that we can transfer the full power from this one to this one and this one to this one. But then we noticed if we do that, when if you're doing a low power charging, the system becomes a little bit unstable. So we investigated different, and we came up with a control methodology, which I don't have the details of it here, but if you're interested, I can provide more information later how to do that. And then we redesigned our board. So this is a new board that we are in the process of building in the lab, which, as you can see, it's designed for manufacturing. So this is the EMI stage. This is the PFC stage, goes through DC link capacitors. This is a transformer that we have a very nicely designed planar transformer. And then it has 2 outputs. One of them your high voltage and then your low voltage side. This is the low voltage switches and these are the high voltage switches. And this is the bottom of the board. You can see all the components which are surface mount on the back of the board. All the power components are in the front of the board. So it's very easy for manufacturing. And then the volume is 5.3 liter. If you compare this to any commercially available onboard charger, this is one charger and one auxiliary power module. Together is smaller than one onboard charger by itself. And then this is the packaging. Now we are working with people in mechanical engineering department, so they're helping us with designing the thermal management of this system. So as you can see, it's a nicely designed package. It's a die cast and it has the liquid cooled die cast. So we are right now working. It's not finished yet. The goal is the whole thing will be less than 7 liter at the end. And again, if you want more information, I can give you later. And the goal is to take this to the next generation. LG is interested to look into this and maybe incorporate for their customers. LG designs these onboard chargers for Chevy, I think Bolt, and many other cars in the US. So that's one of the research areas that we have been working on, the integrated low power onboard chargers, integrating onboard chargers with the auxiliary power module. We also thought about doing another looking into other ways of integration. Again, one of my goals in my research is to how we can integrate different power converters on board of the car and make them smaller, more efficient, and more power dense. So another thing is how we can integrate high power onboard chargers. If we look at the propulsion of an electric car, we have a onboard charger for slow charging, overnight charging, and then we have an off-board charger. This is a high power charging, let's say 50 kilowatt, above 50 kilowatt for fast charging. You go to a charging station and quickly charge it. So we thought, again, you already on board of the car, you have let's say Tesla Model S has a 185 kilowatt hour propulsion machine there, 100, and then you have a DC-DC converter, really high power. So if you design an onboard charger of any kind of charger, what are the main contributors to volume, to the size? Passive components, inductors, capacitors, and then cooling. Switching components are not that big in comparison to these passive components, especially if as the power goes up, your inductors become large. So if I can use this propulsion machine and reconfigure the path and use this as a power, at these windings as the power factor connection inductors, we can charge the battery. We can charge the battery through this only. We eliminate this. These are expensive. Off-board chargers are expensive right now. Right now, the only company which is losing money and paying these out of the pocket is Tesla. But do you think GM, Ford, Chrysler, all these other car manufacturers, they're going to go pay for fast charging stations? No. Who's going to pay for them? Maybe people who own gas stations, they need to own charge stations, right? They invest tons of money, and then they start charging people for charging their cars, right? And then they make money out of that. So one way is, if we can get rid of these and integrate these inside the powertrain. And the only thing that we would need is three-phase outlet. Just the outlet, EVSE. Only thing we need is an EVSE. EVSE is electric vehicle supply equipment, not the whole charger, whole off-board charger. Then we can reduce the cost a lot, and we can help to facilitate deployment of electric vehicle and facilitate of the off-board charging. This could go, the input could be 208 or 480. It could be either one, 408. But we cannot go to MVDC, of course. But there should be definitely a transformer if you want to step it down from MVDC. But it could go, again, the input could be 208 or 480. Not
208, I mean, it's safe. I mean, I guess 480, you can probably argue that.
We can go up to, let's say, I mean, we can go all the way till power. We cannot do 350 kilowatt fast charging. You know, that's not possible. But we can at least increase the power level. And to be honest with you, I believe, do we need to have 350 kilowatt fast charge station everywhere? I really don't think so. How many times am I going, if I have an electric car, how many times I'm going to charge my car battery with 350 kilowatt? Barely, except if I'm traveling from DC going to New York City, or maybe. In fact, it's 300 miles, one charge is enough. But if you're going from DC to San Francisco, maybe a few times on the road you need to charge this. But otherwise, I think your onboard charger, if it's, let's say, 11 or 22 kilowatt, it's good. 11 kilowatt is good enough for your home. You charge it overnight, go to your work and come back. You don't need beyond that. If you're doing really high power fast charging also, you're reducing the cycle life of the battery as well. So, I mean, if we can integrate this could give us a lot of opportunity. So in my research group, because we had a very good conversation this morning with Arijit, and we were talking about, I was thinking that other people, they have looked into this problem. We are not the only group to look into this. People have thought, okay, how do we use this? One of the methods is to have the access to the midpoint of the windings and convert this to a single phase charger, which is possible, I agree. But in my opinion, it's limited power. Single phase is still, the power is limited. If I want to do full power charging, we want to go three phase. And if you want to do three phase, there are one way, if you actuate three windings with 120-degree phase shifted current applied to them, you're going to actuate the motor, and when you're charging, you're going to run the motor. You don't want that to happen, right? So you need to find a way to not create rotation, right? So some people, they have said, okay, if we have access to the midpoints of the windings, right, the current will flow from inside one of the midpoints of the winding, and then current will be split between the windings, and the fluxes will cancel each other. That way, you can prevent the rotation. We thought, okay, can we enable this without having access to the midpoint of the windings? So we came up with a method. I don't have the method presentation here, but we have also we have two papers on it. Again, if you're interested, I can send you the detail of the paper. So we only need to have access to the 3-point terminals, but we need to put an interface here. This interface is a very simple rectifier, active rectifier, which consists of the switches, let's say IGBTs or silicon carbide MOSFETs or whatever switches. No passive components, and we can still use the motor windings as the power factor correction filter inductors. And then we designed initially this prototype, 3.3 kilowatt, and we tested in the lab. And then we designed a new one. This is a 10 kilowatt version. And we tested with the propulsion machine, and we ensure that the rotation doesn't happen during charging. I mean, there's going to be a slight rotation at the beginning till the rotor aligns itself with the stator and then locks at an angle equal to P over, I think for a 4-pole motor is 12.5 degree. So it will be slight and then it will lock. It's not going to be a full rotation.
So this is the PM rotor?
This is the PM, yeah. But any kind of thing, it will not create rotation. It will lock itself at some point. But this is applicable to other kind of machine like switch reluctance motors or to induction motors as well. Again, I'm very much interested to see this technology coming to market. I heard some companies in Europe, they have been looking into using this technology, but there is one barrier for this technology, and that's the fact that even though, let me just go through this and I'll tell you. Let me go back.
That means that when you connect that, you'll get a little bit of a bump or something, right?
When you connect it, like it's a very small, and then stop. Yes, small. It's not gonna move the car, not. But you will only hear it bump. Not, you won't be a motor.
It'll move a little bit, no?
I don't think so. We have done in the lab. We have connected to a motor drive system, and it's like like, it doesn't even take like, 1 second.
Right.
Yeah. But we haven't tested the real car. But one more important than that, in my opinion, is the fact that if you look at the standards for SA 1772 or any kind of charging standard, they do not mandate any kind of galvanic isolation, right? But if you look at any onboard charger, not any, majority of the onboard chargers, they have galvanic isolation there. Here, in this structure, if you're integrating the onboard, there is no galvanic isolation. So people can argue that all you need, you have a huge DC connector here, DC break with the battery DC connector, that can act as a safety thing, but it still is not galvanic isolation, that galvanically isolated. One method is to put a galvanically isolated DC-DC converter here, instead of having a non-isolated, which could potentially be a little bit expensive because of the transformer, right? Another thing could be, people have looked into two stator winding motors there, or maybe, I don't know if you can, I don't think that you can use rotor and stator windings in the case of induction motor, but that's an area which, Arijit has better understanding than me. But there are areas that we can still work. There's a lot of work needs to be looked into in this area before this could be, come into real reality. But anyways.
One quick question here. Why is that kick? Why is that kick which happens? Is there a fundamental reason for that kick?
Yes. We looked, okay, here's the thing. So if you look at the way that we have the current flow here, so for example, the current goes inside from one of these and distributed between these two. If you look at the flux for this winding, look at the current, because the current flow in these windings will be reversed, because the current goes in here and then it splits between these two windings, right? We have, if you use the right-hand rule and look at the fluxes, you would see that these two fluxes, they're not going to be aligned, but there will be a small, depending on the number of the poles of the machine.
So you're
movement.
having a DC flux in a machine?
Yes, exactly. So again, this is area which we are still working on it. We don't know.
Couldn't the problem to kill the magnets or something?
Why will it kill magnets?
I don't know. You reverse the polarity of the magnets.
No, but this is on the stator side, right?
It's only the stator side, not magnets. Yes, only stator side. So anyways, we're continuing this. We have some papers. Now let me, because I have only another 15 minutes to finish this.
No, actually, probably less because we have, there is a class here. So
Okay, I'll finish in 5 minutes then. So another area that we are working is no problem, is megahertz level chargers. So anyways, if you want to reduce the size of these chargers, we need to go megahertz. This is a converter we designed in the lab. This is it's a 3.3 kilowatt. This is only the CLLC stage. On the DC-DC stage, it can go up to 1.35 megahertz level, and it has an efficiency of 97%. It's under revision, and we are trying to publish this. And I think this is one of the highest power densities that we have looked into. Again, this is all gallium nitride based. Other selected project, I'm just going to go briefly show them what are the other stuff we've done. So one of the projects we've been working with the Boeing with the last 5 years is we have been working on the RTRUs. RTRUs are regulated transformer rectifier units. So inside the car, you have a 12-volt battery. Inside the plane, when you sit, you have a 28-volt system, right? All these auxiliary loads, they run out of 28-volt system. But the output of the jet engine, which is coupled to a generator, is a variable frequency, variable voltage, a voltage which you need to rectify it and then go through, DC-DC stage to 28 volts. So this is and the most complicated, and one of the most complicated part of it is the compliance with DO160F, which is the avionic EMI standard. It's very difficult to do that. So we designed this and we comply with all this DOE160, and then these are some of the results. You can see this is the AC-DC boost rectifier, DC-DC phase shift full bridge with a center tap transformer at the output, and we showed all the efficiencies, and then that's the EMI stage. This is the overall topology. Now we are working with the Boeing. This is an improvement of 8% efficiency, which is a lot, 8% efficiency over what they use right now, and then reducing the weight by 50%. Right now we are designing the modular gallium nitride version of this to reduce the size by another 30% and improve the efficiency at the full load by additional 1%. Somebody told me don't talk about efficiency numbers. 1% efficiency doesn't impress anybody. Talk about improvement in loss. You can say you're reducing loss by 50%. That's much better number. We did another project for a space company. It's a gallium nitride-based DC-DC converter for space application. This is designed for maximum power point traffic maximum power point tracking, and in the space application, they tested this from negative 120 degrees Celsius up to 120 degrees Celsius, and then I think it failed after so many thousand cycles. But the failure was not because of the gallium devices, gallium nitride switching device. It was because of the failure of the microprocessor, microcontroller, because of that low temperature. It didn't work. We also worked on miniaturization of power electronics for biologically inspired micro robots. This is a complicated stuff that we did. I think 1.5 megahertz we did for a tiny jumping and walking robots. These are the inch-worm motors. In fact, one of my colleagues, that she designs these micro robots. But if you look at these micro robots, robot is like so small, but their power supply intends to be larger than the robot entirely itself, because you need to have a tiny battery voltage, step it up to, let's say, from 2 volt to 150 volt, and then convert it to a sinusoidal or an inverted to something to actuate it. These two stages, they tend to be really low efficient in low powers, and then they tend to be large. So one of the areas we've been looking how we can integrate these to a single stage and highly efficient, and improve all the characteristics. So we designed this, we tested under microscope, and we saw good results. Now we are looking into writing proposals to different agencies, get funding to really implement this on board of a robot and show the real autonomous operation. Another project, it was again miniaturization for electromagnetic energy harvesting. We also did some work on pyroelectric energy harvesting, and we showed for the first time that we can harvest power and charge a battery using pyroelectric energy harvesting cycle. So pyroelectric energy harvesters are similar to thermal materials. So you need to charge that material up to certain voltage. You need to warm it up by laser or something if it's in the remote location, and then you need to discharge it, and then you cool it down. In this process, you can harvest power to actuate a sensor node or anything. So this was, again, as I said, first paper we designed it for 10 milliwatt. We showed 55% efficiency, which is really good for this kind of power level. And then we showed that we can charge a battery, and published in Applied Energy Journal.
Is pyro a fire thing?
Yeah.
Thermal, yes, exactly. It comes from the thermal, yeah. Exactly. Also, we work with a company called Genovation. The Genovation designed the world's fastest electric car with a top speed of 220 miles per hour. And this car initially was supposed to have not only a battery, but also battery supercapacitor. It was designed for performance, right? So again, now this is the C06 model. They are designing the 07 model. Again, that's one of our collaborators. I was going to talk about the hybrid energy storage concept here, but we don't have time. I'm going to finish it here, and I would like, before I finish, I would like to thank all our sponsors that they have funded my research within the last 7 years. Thank you for listening to this.
220 miles per hour.
220 miles per hour. That's the street legal.
Bugatti then, hopefully.
They are the fastest electric car in the world right now. Electric.
Yeah.
Not, yeah.
Bugatti Veyron Super Sports is around 257 or 263 is the highest recorded.
Wow. Yeah, these guys are selling this car for $750,000. I don't know I cannot afford, of course, but I don't know. I'm sure there are very.
So it's okay. Mill.
Yeah, I'm sure there are. I know Bugatti is the most expensive one. Yeah.
They're in the running for.
We can buy for research from NSF fund.
Oh. I don't know.
One question.
Sure.
So I have read in the literature, this is not my experience,
Sure.
and based on whatever I read, that dual active bridge is supposedly more efficient compared to LLC in bidirectional power conversion. Is that what your experience is?
In my opinion, depends on the power level you're designing it. If you're below, let's say, 5 kilowatt, CLLC gets better efficiency numbers. But if you're above 5 kilowatt, I think dual active bridge is better. We have, in fact, one paper we showed, we didn't show exactly what is the threshold, but in 1 kilowatt, we designed 4 or 5 different converters, and we compared them. CLLC was still better than dual active bridge in 1 kilowatt. But when you go to high power, I think it's power, then dual active bridge is better. But the reason we use dual active bridge is not because of efficiency in this project, because dual active bridge or triple active bridge, it's easier to control the power flow because you have phase shift and pulse width modulation as opposed to pulse frequency modulation. We couldn't design and control the dual output from LLC topology. We in fact tried different options. We looked into CLLC, and also we looked into current doubler in the output, in the tertiary one. We looked a lot of kinds of methods. We noticed that triple active phase shift is the only one that we can control both outputs simultaneously with a minimum circulation current.
And all your LLC topologies are bidirectional in nature, or is it like, can we go from vehicle to grid? Is that doable, or?
Yeah, all of them. We try to do bidirectional because I believe it's the future. It's a research level. If we want to design something to sell in the market, I don't think we would need to do bidirectional. It's most probably unidirectional will be cheaper and more. But because we're doing research. Yes. Yeah. Yes.
You work with that guy over in Czech down at the Wolf Company?
With Wolf Speed?
Yeah, Wolf Speed.
I mean, to be honest, we buy all the time with their switches. Yeah, we haven't worked with them much, but we.
Sponsor your research?
No, we don't have Wolf Speed as our sponsor. Maybe one day.
Someday.
Sure. We have also some companies recently which I forgot to include them, but in future. Thank you.